Good afternoon, everybody. This is Dr. John Galbraith from Virginia Tech. I'd like to welcome all of you to the advanced version of our webinar series. Today we'll be talking about chemical weathering of soils and parent materials. And I just have a few housekeeping reminders. The first thing is that I'd like to ask everybody to mute their microphone automatically when you log in. And this eliminates the background noise and keeps it a cleaner presentation for everybody. And also as well, we're going to ask people to introduce themselves today. One thing that happened yesterday, we had a nice webinar series 2 days ago, but we had no chat. And I really do think that the chat part is a nice part, a nice feature of these webinars, and I'd like to make myself available to you. So right now, the people that are logged in, there's about 8 people logged in, and if you don't mind, turn on your chat feature and then just let everybody know who you are and where you're from. And you don't have to give too many details, just get it started. So who would like to go first? I see that David, a couple of Davids, Doug, Megan, Wendy, Pete are signed in. Where are you guys from? Northern Virginia, or South Side? Oh, good, Megan. Oh, and I got your email today, and thank you for sending that. So Megan's from Hampton. My daughter lives in Newport News, Fairfax County. Good. Okay. See that Julie and Lloyd just joined us. Oh, good. David is a naturalist for Northern Virginia Parks. Very good to have you. And all right, I see Tamara is raising her hand. I guess I'm not the best to know what to do when you raise your hand. I'm hoping that means you're just in the process of connecting. We typically get started about 12:05 on these webinars, so and I notice that a lot of people do log in between 12 and 12:05, and we've got plenty of time because this session has only got about 26 slides, so we'll have time to discuss it. The session will be recorded, and then we will save the recording. It'll be a streaming video, and we'll post that on a website. And one thing about the website is that you'll be able to, let's say that you miss out on one of the webinars and you'd like to get caught back up, then you can go to the Virginia Cooperative Extension website, and they're establishing a page right now. It should be up any day, and then you'll be able to look under the list of all of the webinars and then just click on the links that you'd like to view, and it'll have the slides and my voice. I do not know whether it'll include any of the chat questions or not, but it should include anything that I verbally say. And I see Wendy Mills from the Nature Conservancy is here. Welcome, Wendy. All right. I am going to also post something here on the chat. I have developed a survey tool that allows people to tell me what kind of information they'd like to get. So if you need something that's more specific to your job and have a request, well, I've set up a site where you can let me know that. So I'm going to post that web link and make it available to you during the presentation, and then we're going to go ahead and get started. So I'm going to go ahead and put that in the chat box. This is the survey, to let me know what your requests are for webinars, or it could be on-site training or other training. Okay, so that website should be going out to everybody now. Oh, I'm sorry, I did a typo there, but please forgive me. All right, well, let's go ahead and get started on the webinar for today. We're going to talk about chemical weathering of soils and parent materials. And a lot of this will be a discussion of the processes that are involved. And we're not going to go, this won't be a full soil chemistry course, but it should cover enough of the basics to hit the major types of chemical weathering that are going on around you. One of the things I really would like to do is make this relevant for you. And so that'll be our first step. Now, hopefully when you got the invitation, it gave you the choice to either call in or to call in using your computer. And I noticed there might be some people that are trying to log in or call in that are having trouble getting connected. So I typically just log in, call in using computer, and that should come up when you register and hit the link that was sent to you that confirmed that you were part of the webinar series. Okay. So we have two major types of weathering that go on, and physical weathering is a different webinar that we'll cover in much more detail. But you can see the picture in the upper right-hand side. This is an example of physical weathering. Here's a boulder that's been isolated in a glacier field, and you can see how it has cracked apart. And this physical weathering, the biggest part of physical weathering is the unloading of pressure that allows rocks to come apart along cracks, between crystals, along cleavage planes, and separate into smaller pieces. Now, once those rocks separate into small enough pieces, then they can be moved and removed from the area. As you can see that the smaller pieces are being moved away from this large rock. But you can also notice that there is weathering going on along some of these interfaces and macropores between the fragments of rock. Okay, what we're going to talk about today is the decomposition or the chemical weathering. And it begins before, during, and after physical weathering. And one way that we know that it takes place before physical weathering is that you may look at a rock such as this fragment here and think that it's a solid piece, solid as a rock, right? But really then if that rock fractures along a cleavage plane or between crystals, and you see a cleavage plane developing right here, you'll probably notice that there's a weathering rind on both sides of that. Secondary minerals being deposited. So some of that chemical weathering begins before the rock begins to come apart. Some of the weathering takes place later, and you can see the coatings on the outsides of this rock and indicating that secondary minerals are being deposited here. Here you can see what's called a trim line, and you can see that probably this is where the rock was buried in sediment, and there was much more chemical weathering going on underneath the surface than there was above the surface. So this one rock, this one picture tells us quite a bit about these processes. To the right in the lower part of the screen, you see chemical pitting of carbonates. Now, I noticed that somebody does not have their microphone muted, so if you wouldn't mind muting that, that would really help all of us. I'd certainly appreciate that, and the rest of us would as well. because these microphones are very adept at picking up background noise. Well, let's talk about weathering in a humid soil. And the reason I picked on that is because weathering in drier environments is quite different. And so we're going to make an assumption that we're weathering materials in an environment that's wet enough for chemical weathering to occur, and that also we have enough warmth to drive the chemical reactions, and that we have enough leaching to remove the weathered byproducts. Later on, we'll discuss what those byproducts are. But if we can remove the weathered byproducts, then we can keep the weathering process continuing in its current state. If the weathered byproducts build up, then it slows down the chemical processes. Okay, so what does chemical weathering do? Well, it decreases the particle size, and I've shown this arrow to show that if you decrease the particle size, you increase the surface area. And there's a graphic that I borrowed from the internet, and it shows two pieces of material. They both have the same volume. It's just that one of them is broken into 8 fragments. And they both have the same mass. But what they have that's different is the surface area. By breaking this from 1 fragment into 8 fragments, we have doubled the surface area. And the greater the surface area, the more area that's exposed to chemical reactions. Okay, so for other decreases, well, if we decrease the bulk density by removing mass from the middle of these rock or soil particles, the mass in between the skeletal fabric is called plasma. And so what remains behind are the sand grains and the rocks. The plasma is removed, and that decreases the mass and increases the porosity. In this case, the macro porosity, or the cracks between individual fragments, has increased in this example. But we also get an increase in internal porosity through chemical weathering. Okay, well, we can also decrease the cementation between particles. We can decrease the stability of the primary minerals that make up the particles, and we do this by breaking bonds. Well, another thing that chemical weathering does over time, the CEC and the base saturation decrease, and so does the pH over time, unless something changes to offset that. Okay. So increases besides surface area and porosity, we get an increase in clay and other secondary minerals. So what we do is we go from primary minerals, and through chemical weathering, we develop secondary minerals. Clay is the most important secondary mineral that we form, and soils are said to be clay factories. Another thing that happens over time is we increase the soil depth through chemical weathering. All right, just again to reiterate the difference here, here's physical weathering has broken or allowed these individual fragments to separate. Once they have separated, you can see a weathering rind that's developed around the edges. This weathering rind is chemical in nature. This part of the rock is aerated, exposed to oxygen. The internal part of the rock has no porosity, and so it is essentially oxygen-free. Here we see granite that has begun to weather from the outside in. So in other words, imagine each one of these being a weathering rind. And eventually we get to the core of the rock that's still dense and without pores, but the porosity has begun to develop in these weathering rinds. And these are those fracture planes or cleavage planes between the rock fragments. And this is before the rock has become separated. Here we see a rock from the desert, and we see that chemical weathering has already produced secondary minerals on the outsides of this rock. And I think if you look closely at this crack, you'll see that that it's a different color, and it's not just a shadow. There are secondary minerals, primarily iron and manganese oxides, being deposited between these rock fragments, even though the rock fragments are still in their original position. And there's some nice petroglyphs here as well. Okay, well, let's talk about equilibrium, because that's fundamental to understanding what the controls are on chemical weathering. So weathering proceeds until it reaches what we call a dynamic equilibrium with the conditions in the soil. If we change any of those conditions, either by changing the forces, the temperature, the heat, the pressure, or we might change the soil, the position of the material in the soil profile through erosion or burial, or we may have a climate change. If any of these things happen, then weathering is not only altered, but often rejuvenated. Now that's chemical weathering. So here we see where the changes from one chemical to another are equal and offsetting. And so this would be said to be at equilibrium. If we change one of the vectors so that there's much more of element B changing to element A, then we change the equilibrium, and it rejuvenates chemical weathering and forces more of A to go to B. All right, well, where's the intensity of chemical weathering the most profound in the soil? Is it down deep, or is it near the surface? And this graphic lets you know that I feel that it's near the surface, because there's more air exchange, there's more carbon dioxide leaving the soil, and more oxygen entering the soil, and that is not true at depth, mainly at the surface. We have dynamic temperature changes, and we're going to experience some of those this weekend. The high in Blacksburg on Sunday is supposed to be 17, and the low is supposed to be 3. So we're going to see some of the soil at the surface is definitely going to be affected by that. Frequent wetting and drying, because we need moisture to drive these chemical reactions. Frequent eluviation, and that again is the process that removes the weathered byproducts from the surface. And so that we have the need, then I guess it takes it out of equilibrium and then allows chemical weathering to be rejuvenated. So does that make sense? If we remove the weathered byproducts from the surface, and it happens most often at the surface because that's where the wetting takes place most often. A lot of our rains don't wet the soil up to 4 or 5 feet, but they may wet it up thoroughly in the upper foot. Well, that material takes the weathered byproducts, moves them out, that disrupts the equilibrium in the surface, and then rejuvenates the chemical weathering. Well, we have plant growth, and these plants uptake nutrients, and that disrupts the equilibrium. The plants release organic acids from the leaves and from the roots, and these acids rejuvenate weathering. Chelation is one of those. We have microbiological activity, which is most intense in the upper 6 inches of the soil. And those microbes release gels, they uptake nutrients, and they break bonds. And then we have frequent and intense cycles of freezing and thawing and mixing of soil and movement of particles. And you can see that all of that takes place most often at the surface. Well, which soils in Virginia weather the most easily? Well, I'm not going to name individual soils. Let me just explain a concept. Soils that receive water that percolate through them at a moderate or a rapid pace and leach out the weathered byproducts. Those are going to weather the most easily. If there is a restrictive layer in the subsoil, it will restrict the weathering. Soils with fluctuating water tables do not become saturated with the soluble byproducts. And that, if they did, then diffusion would come to a halt. But if we can fluctuate the water table, then when the water table drops, it takes the soluble byproducts with it, and then that rejuvenates or disrupts the equilibrium and rejuvenates the chemical weathering. And then soils that have easily weathered parent materials are going to weather most readily. And so that would be parent materials that are low in quartz, low in iron and aluminum oxides, and high in unstable primary minerals. There's a whole bunch of primary minerals in a soil, but some are more stable than others. And this is a graphic that I borrowed from this not very good website, very good. And it shows the stability of these minerals in the soil. Now, not all these are primary minerals. Pyroxene is a primary mineral, biotite, muscovite, but clay is a secondary mineral. Quartz is a primary mineral. Gibbsite and hematite are oxides. This is an aluminum oxide. This is an iron oxide. And I'm sorry, it was aluminum hydroxide. And so you can see that the stability increases toward the bottom of the chart. If these are the most stable, they're going to be the ones that slowly weather. The ones that are unstable are the ones that are going to weather the most rapidly. Well, here's a graphic that just shows that weathering starts to take place before the material is exposed at the Earth's surface. And so we have these deep cracks and faults and fracture lines and places that water can enter and begin the weathering process well before the material is exposed at the surface. And here's another picture, and this would be more of a granitic or igneous material where we actually start to weather the rocks from the outside, and so that by the time a soil scientist comes along and digs a hole, they see a rock in the middle. They don't realize that maybe the rest of this material used to be a solid rock, just like it was on the right-hand side of the graphic. But this is pretty useful explanation, I think. All right, we're going to launch into the chemical processes, and then we're going to stop and take questions. So the first one is just hydrolysis, and it's the most common. And it's where hydrogen substitutes for a positive element inside of a mineral, and that causes mineral instability. And so a hydrogen would typically substitute for another element with a valence of 1, but it can sometimes, multiple hydrogens can replace elements with higher valence. Okay, we also have dissolution. And the best example in Virginia of dissolution is carbonation. And that's where we add carbon dioxide and water in the soil to form acids that dissolve carbonate rocks, carbonic acid. Okay, we have uptake and extraction. And this is done not just by plants. It's actually 2 different processes. I probably should have split those. But uptake is where plants uptake nutrients from humus and clay, and that causes instability if enough nutrients are removed without being replenished. And extraction can be done by fungi, bacteria, and archaea, and they can extract the elements directly from the rock as an energy source, and of course that causes instability in the crystals. Oxidation and reduction is just the gain or the loss of electrons. That changes the solubility and insolubility of the elements, and the soluble elements may be lost from crystal structures when that element is reduced, or they may become leached or eluviated in the groundwater as a soluble byproduct. And then hydration is the last one, and that's where minerals take water into their crystal structure, and that changes the volume, and that leads to instability. So let's look at hydrolysis here, and I was trying to show by this graphic that you need the presence of water. One of the hydrogens disassociates from the water molecule and replaces an element that's attached to this compound. Now this can be a clay particle, it can be an organic matter, it can be anything in the soil, it can be the edge of a rock. And this material then takes the place of the hydrogen, so they switch. Well, what that does is it changes the crystal structure. This one doesn't show to be changed, but these bonds are under strain. And when the bonds are under strain and stress, they often weaken and then come apart. And in this case, the replaced element took the place of hydrogen, formed a new compound, and often those are soluble. All right, let's take a look at this example here. This is part of the carbonation process where the hydrogen takes the place of the calcium and produces a new mineral and kicks the calcium out, and that begins to dissolve the carbonate, which makes up most of our limestone. Let's look on the right-hand side. Hydrogen splits from water, replaces an ion, and the replaced element combines with the hydroxyl to form a new soluble compound. So here we have two hydrogens coming off of a water molecule. So there are two water molecules here. So we pull one hydrogen from one molecule, one hydrogen from another molecule. We have two hydrogens. They come over here and replace the two potassiums in this feldspar crystal. Well, that weakens the feldspar crystal, and it starts to become a different mineral. The hydrogens take the place of the potassium, and the potassium is kicked off and then takes the place of the hydrogen. And then the potassium hydroxide is leached. And the second, we're going to talk about carbonation as the form of dissolution. Here's a picture underground, and you can see that groundwater is moving down here. So we have two things going on. We have the chemical weathering here, but we also have weathering down in these places in the cracks where they may be filled with water, often are, the cave system. And there, if we increase the parcel pressure of carbon dioxide, we also can do chemical weathering of the carbonate. But by both of those chemical processes, we end up developing cave systems, and then the water comes up under pressure in the lower part of the landscape. This is what that looks like when you exhume it, or literally weather and wash all of the loose weathered material away from between these limestone fragments. Okay, well now would be a good time to open this up to chat. And I'd like to invite any questions about some of the previous material that we just talked about. All right, let me see if I can ask you guys a quiz. Which of the processes do you feel was the most common? So of the ones that I covered, hydrolysis, dissolution, uptake and extraction, oxidation reduction, and hydration, which do you think was the most common? Hydration. Okay, that's actually at the bottom of the list. What's at the other end of the list? The one that's named first. Yeah, exactly. Hydrolysis, because that's the one that I named first. A question came in, and it was different, and it says, what is archaea? Archaea are a microorganism that were once thought to be bacteria, but they're now are put in their own family. And so they typically, a lot of archaea live in the soil, and they partake in, they can live in anaerobic conditions. They can live in extreme heat and extreme pressure and temperature. So, for instance, also in extremely saline areas. So archaea are, and the word archaea comes from archaic, which means old. They're thought to be some of the most primitive life forms on Earth, and probably evolved about the same time that bacteria did at the beginning of time. All right, well, let's go ahead and finish the chemical weathering. Thank you for the questions and the answers. Well, let's look at uptake. Well, we have plants and we have minerals in the soil that are attached to the clay or attached to humus, and those minerals then are drawn in by roots, and attached to the roots are fungal hyphae. And the fungal hyphae extend way out into the soil beyond the root system. They uptake these minerals and they're taken up into the leafy plant parts. Here's another picture, and it shows elements that are attached to clay particles or organic matter or to minerals in the rock. And the hyphae here of a fungus is growing toward this source, and it is both uptaking metals, minerals, and nutrients into the plant. And of course, if you remove elements from the edges of these minerals, then it disrupts the stability of the mineral. Here's an example of extraction, and you can see where the lichens here have been growing right along the cracks in this large piece of bedrock. And you can tell that they have been growing, probably started in the center and then grew outward in an ever-increasing size. But take a look, and these materials contain fungi, and the fungi are able to extract nutrients directly from the rock. So you can see that as this growing front moves away from the original center, you can see that it left the rock different in appearance than the rock to the outside. And so that indicates that the fungi was removing elements from the rock as it grew away. Here's oxidation reduction, and here's two neutral elements in the soil. And let's see what happens when an electron goes from element A to element B. So they start out being neutral, but then A donates an electron to B. Well, if A donates an electron or loses an electron, it becomes more positively charged and is said to be oxidized. If element B accepts the electron, then it becomes reduced because the overall charge is reduced by adding a negative. Often these are crystalline forms when they're oxidized, and often they are soluble and non-crystalline when they become reduced. Well, let's talk about redox potential, and that's the potential of the soil of the element to either gain or lose electrons. And we can see by the graph on the right that in aerated environments such as streams, rain, atmosphere, and whatnot, we have much less oxidation potential and redox potential. As we get into more anaerobic environments, we have a greater potential for redox in the soil. So these are reducing conditions when it's aerobic, and they're oxidizing conditions when it is aerobic. And pH does play a part in it. So oxidation and reduction are more likely in soils with lower pH and more oxygen. Well, here's some pictures of hydration. And you can see this background rock, and you can see these crystals that are growing out of the rock. Well, what's happening is they are becoming hydrated. They are absorbing oxygen in between the other bonds, and it breaks bonds and it spreads the elements apart and increases the volume. So here's water. It comes in, it disassociates and attaches to this original rock, and then that forces the rock apart by the expansion factor there, and then that causes instability. And here you can see where water has entered some of the cracks in the rock and dissolved some of the calcium and sulfate, and now hydrated calcium sulfate, which is also known as gypsum, is starting to precipitate on this rock, but instability is occurring. Well, what happens to the soluble byproducts? Because if we don't remove those byproducts, then we reach an equilibrium and chemical weathering stops. We need to have diffusion, and we can't have diffusion if we reach equilibrium. So many of the soluble elements are temporarily adsorbed onto charged surfaces, such as humus or clay particles. And then here's a root trying to uptake some of those elements or donate some elements. And so they're taken up by plants and recycled into the litter layer. Here in the tropics, it's especially apparent. The leaves fall off the trees, hit the litter layer, they're quickly decomposed, are taken right back up by the tree roots into the tree. And so oftentimes the nutrient cycle in the tropics actually is restricted to the above ground biomass and the leaf litter layer. They don't often use the soil for much more than water uptake and structural support to keep from falling down. Of course, we can also lose soluble elements by leaching to the groundwater. Well, what about insoluble byproducts? Well, a lot of those insoluble byproducts are charged, and so they're temporarily adsorbed onto charged surfaces. And then they're lost from the system if we lose the soil. So they go with the soil that they're attached to. Here we see erosion. Here we see human excavation. If we erode or if we excavate, we rejuvenate the chemical weathering. I'm not trying to justify that, though. All right, how about controls on weathering? Well, soil depth would be one. So the deeper we go into the soil, the less weathering there will be. There's a thin mantle of soil up here at the upper part of this rock outcrop, but no, you can still see the rock structure in the center of this ridge and valley road cut. This is in Pennsylvania. And here you can see where the solid bedrock or consolidated bedrock occurs, and all of the material above this is unconsolidated because the chemical weathering has thickened the soil. Well, you can imagine right here where this bedrock comes closest to the surface, it's still within the realm of the chemical processes. But the bedrock that is here in the center of the mountain, it is not really exposed to those chemical processes. It's insulated. And so there's not much chemical weathering going on right here. Okay, hydrolysis is the major chemical reaction, and it requires hydrogen ions. So a higher pH or a drier soil limits hydrolysis. Higher pH soils have less hydrogen in them, and drier soils have less water that disassociates into hydrogen and hydroxyls. And so therefore weathering proceeds faster in moist, acid soils. Well, here's climate. So chemical weathering increases if the moisture and the temperature are high, like we find in the tropics. Now, take a look at this, and what you'll see is that the first layer of actually consolidated material occurs down at this depth. And the material above here is already pre-weathered bedrock. This material is called saprolite, and it no longer is cemented, and that's why it erodes so easily. But you can see how deeply the saprolite is below the soil. And using this gentleman as a scale, this is where the consolidated bedrock occurs. So you can see how deeply the weathering front can take place in warm, moist places. Well, chemical weathering decreases as moisture decreases regardless of the temperature. This is a hot, dry area. It has the heat, but it doesn't have the moisture. So weathering is minimal here. And from this graphic, I want you to take a look and track the precipitation versus the temperature. Versus the evaporation. So when precipitation exceeds evaporation, we have chemical weathering. Where evaporation exceeds precipitation, we have minimal chemical weathering. And here in the tropical areas, the precipitation greatly exceeds the evapotranspiration. And so we have the deepest weathering taking place because this is where the maximum difference between evaporation and precipitation is. All right, here's another control on weathering. We talked about removal of byproducts being necessary to rejuvenate the weathering process. Otherwise, it reaches stagnation. And so if this groundwater becomes totally saturated with the same elements, then there will be no diffusion of elements from the soil into the groundwater. And so weathering comes to a screeching halt. If we can drain this area, and I'm not advocating that because I'm a wetland scientist, but if this water table fluctuates through climatic change or just drought or just summer temperatures, then we rejuvenate the weathering of the soil that surrounds this area. Here's one of the effects, and that's topography. So summits, terraces, and floodplains are all very flat areas, and they have very effective precipitation. So if an inch of rain falls on the summit, an inch of rain soaks in. If an inch of rain falls on the floodplain, an inch soaks in. If an inch of rain falls on the shoulder, half of that is going to run off. And so it's going to collect in these lower positions, like the foot slope or the floodplain. So the effectiveness of precipitation as determined by the topographic position is a control on weathering. The more water that comes into the soil and through the soil, the more chemical weathering we have. Here's where aspect plays a difference. And this picture is actually taken in Scotland. And you can see the side of this hill that is facing the sun all day has grass vegetation, grass-like vegetation. And the side that is facing away from the sun most of the day has a shrub or a heath vegetation. So in summary, then, in Virginia, we have a temperate climate, humid climate. It's warm enough and moist enough for chemical weathering in our soil. And in our oldest soils, many of the byproducts of weathering have been leached unless there was something that prevented the byproducts from being removed, and that would be a permanent water table or extreme runoff, which restricts the amount of water coming in, or water restricting layers such as a fragipan. And if we don't have those, then we'll have intense weathering and leaching, and that explains why a lot of the soils of the Piedmont are so very infertile and low in phosphorus and other nutrients unless fertilized. So that's the end of our talk today. I'd like to thank everybody for being here, but I'd also like to open this up for other questions. So are there any questions about the material that was covered or some of the principles? I think that the type of material covered in today's lecture would be one that would help if you're going to be taking a certification exam or looking for CEU credits and attending some training courses. So that's the level that we are presented at today. Okay, let me ask the group a question then. We have two cases. One, it would be a cold, dry area. One would be a cold, moist area. Which one would have greater chemical weathering? The moist one is correct, because we have to think back to the processes that took place. The hydrolysis, absolutely affected by the availability of water. Hydration requires water. Oxidation and reduction is different depending on whether the soil is anaerobic or aerobic, and most of the times anaerobic conditions are caused by high water tables that persist in the soil. And then, of course, we had uptake and carbonation is also affected by moisture. Okay, well, if we don't have any other questions, I'd like to thank everybody for attending today. We'll have another advanced session next month. I would like to say that I'd like, if you don't mind, passing the word along that that these sessions are available. If we really need to have a minimum number of people participating in order for me to spend my time giving these webinars. And if this is not the most effective way, then then we'll offer the information in other formats. So if you'd like to go to that survey that I posted earlier and give me your feedback, that would be welcome. The survey's open right now for data collection. Tell your friends about the webinar series. It's, again, offered at introductory, intermediate, and advanced level. And right now, we had 84 people sign up for the introductory. We had 20 sign up for this level. So that's fine. I think that that's a reasonable balance. But if we find that our numbers drop at the advanced levels, then we'll simply just discontinue the advanced level and offer on-site training for advanced purposes, and we'll do webinars for the introductory material. So in any case, feel free to use that survey to give me your feedback or send me an email or chat. And thank you for attending. I hope you have a wonderful day and have a warm weekend. I'll be out in the field with students tomorrow. Sunday, we decided that 17 was just a little bit much, so we're going to go ahead and work indoors on Sunday. So have a great day, and thank you for your questions and your attention, and I enjoyed it very much.